Madam, please start.
Good morning, everyone, and good morning, dear students. So today is again the chemistry webinar session. It's the time for chemistry webinar, and I would like to invite Mr. ARAVIND, PGT Chemistry from TSMS Ramayampet, Medak District. Sir is again here to explain you the third session of solid state children. So today we are going to discuss about the imperfections in solids. That is the SCOTTKY and FRENKEL defects. So please listen to sir and kindly write the notes. Aravind sir, good morning, sir.
Good morning, ma'am. Good morning. Shall I start the session, ma'am?
Yes. Yes, sir. Please carry on,
yeah.
sir.
Yeah. Thank you, ma'am. Thank you.
Thank you, sir. Thank you.
Thank you, sir. Thank you, ma'am. A warm welcome to all. Good morning, students. Today, the third session of solid state, we are going to learn. Let me recall what we have studied in the previous classes. Let us recall. The space lattice and unit cell, types of unit cells. We have discussed about different crystal structures and Bravais lattices. We have calculated the number of atoms in a unit cell. Close packing of spheres we have discussed. And finally, the most important one, tetrahedral and octahedral voids we have studied. Now, children, today, the most important topics I'm going to explain, let us see in the learning objectives. Packing efficiency, density of the crystal, how we have to find the density, imperfections in the crystals. These are also called as a SCOTTKY and FRENKEL, which is very important, children. Band theory of solids. In that, p-type and n-type semiconductors also we need to discuss. And finally, the magnetic properties have to be discussed in this session. Let us move to the first topic, children. Packing efficiency in the simple cubic lattice. Children, as I've already said, simple cubic lattice consists of the points, lattice points, only at the corners. Yesterday's class, if you go through it, definitely you will be able to understand that the particles are present only on the corners, right? In the cubic lattice, atoms are located only at the corners of the cube, right? Let me go to the packing efficiency, children. I'll tell you what do you understand by the term called as packing efficiency. Packing efficiency is the percentage of total space filled by the particles. For example, total cube if you have, right? In the total cube, I cannot have all the packing cubes. Am I right? So what you have, only the lattice points which are present at the corners will occupy some part, only some part. Let us go this one by one. The particles touch each other along the edge. Thus, the edge length of the cube is A. Let us suppose edge length. Let us say this is edge length. Okay, children, this is edge length A. And if you take this one, children, you are able to see this is the radius R and this is the radius R. I can say, children, A is equal to 2R. Hope you understand, children. A is equal to 2R. Therefore, what is the relationship between edge length and the radius? A is equal to 2R. Therefore, the volume of the cube, as you know, is nothing but A cube. Therefore, what is A, children? 2R. Just now I said. So, A cube is equal to 2R whole cube, which is equal to 8R cube. Right? So, volume of the cube is 8R cube. Now, how to calculate the packing efficiency? Children, you know that packing efficiency have a formula, volume of one atom. Why I've taken one atom? Because in the simple cubic lattice, I have only one atom because all the atoms are at corners only. But you know that in yesterday's class, I was discussing about Corner contribution is 1 by 8. Therefore, 8 into 1 by 8, which is equal to 1. Therefore, packing efficiency is equal to volume of one atom by volume of cubic unit cell into 100. Therefore, volume of one atom, volume of sphere is given by the formula 4 by 3 pi r cube divided by 8 r cube into 100. Therefore, if you simplify it, you will get 52.4 children. Hope you understand. So the packing efficiency in cubic lattice system is 52.4. Means whatever the unit cell total space is there, out of that, the spheres will occupy 52.4% of it. Let me go for the next one, children. 1 second. Let me, please give me a little time, right, ma? Right. Packing efficiency in face-centered cube or face-centered structure. Let me clear this, children. 1 second. Right. In the face-centered cube, atoms are present only at the corners, not only at the corners, but also on the centers of the faces. So the packing efficiency is 74%. Because of the time, we are not able to derive it, but just remember that it is a 74%. Let us go for the next one. Packing efficiency of BCC. This is also 68%. Just I'll give a value, right? Now, overall, the packing efficiency of a simple cube is 52. FCC is 74 and BCC is 68%, children. Let me go for the next one. How to calculate the density of the unit cell. The density of the unit cell is given by the formula Zm by Na into V. You are able to see this, children. Z into M by Na into V. Now, I have to elaborate these terms, what we have used in this. Z is the number of particles present per unit cell. That means if the unit cell is given as a primitive, the Z value you have to take it as 1. If the Z value is 2, it will be a body-centered cube. If Z value is 4, it will be a face-centered cube. Now, M represents the molecular weight of the crystalline substance, and A is the edge length, as I said. Now, volume is equal to A cube, right? Therefore, in the place of A cube, even I can substitute volume also. Next, Na is the Avogadro number. Let us do one problem regarding this. The crystalline sodium has the body-centered cubic unit cell with edge length A is 0.424 nanometers at 298 Kelvin. Calculate the density of sodium metal. Now, children, he is asking to calculate the density of the sodium metal. The sodium occupies which shape he is saying? Body-centered cube. And what is the edge length given? 0.424. Now, what is the formula of the unit cell, children? Z into M by A cube into Na. Now, given it is a body-centered cube, Z value 2 you have to take, and molecular weight, or you can also call it as molar mass of sodium is 23 grams. Now, I am converting this 23 grams into kg. 1 gram is equal to 10 to the power of minus 3 kg, no? The same thing, 23 grams I have converted into kg, which is equal to 23 into 10 to the power of minus 3 kgs. Now, unit cell length A is given as 0.424 nanometers. You know, children, 1 nanometer is equal to 10 to the power of minus 9 meters. 1 nanometer is equal to 10 to the power of minus 9. Therefore, 0.242 nanometer is equal to 0.424 nanometer is equal to 0.424 into 10 to the power of minus 9 meters. Avogadro number, as you know, its value is 6.023 into 10 power of 23. Substituting this value, you will get density, which is 1001.95 units, children, kg per meter cube. What are the units? Kg per meter cube. In this way, this is a model problem I have explained in order to calculate the density of the sodium metal. Right. The very important term, crystal defects, or you can say imperfections in solids. Children, you can ask me a question. What do you understand by the term called as defect? Defect is not any deformation or else, right? Defect is, you know that crystal substance have a regular pattern of constituent particles. I have explained in the session 1. But during the crystallization, there may be the possibility of not presenting at exact crystal point, or dislocating, means moving into another interstitial space. This may be happen during the crystallization of the solids. Now, if this occurs, this particular one is called as imperfections in solids. Now, imperfections are divided into two types, ma. The first one is a stoichiometric defects, you can say. So that's the reason I have given you the heading types of defects, right? Defects also be termed as imperfections, right? Imperfections are divided into two types, ma. The first one is stoichiometric defects and second one is non-stoichiometric defects. Now, what is the major difference between stoichiometric and non-stoichiometric? In the stoichiometric defect, the ratio of positive and negative, means cations and anions, will not vary. It will be same even after the defect also. Hope you understand. After the defect have arrived or formed also, the ratio of positive and negative ions will not change. It will be same. Ratio will be constant. Whereas a non-stoichiometry, there may be variation in their ratio. Now, stoichiometric defects are classified into three types, ma. The first one, vacancy defect. I have highlighted Schottky defect because Schottky defects comes under vacancy defect, ma. That's the reason I have highlighted this with a blue color, which is very important for your 4 marks. Next, second one, interstitial defects. Now, interstitial defects, in that we have Frenkel defects. Frenkel defects also important, which comes under interstitial defects. And lastly, impurity defects. Therefore, stoichiometric defects are divided into how many parts, ma? 3. Vacancy defects, interstitial defects, and impurity defects. Now, coming to the non-stoichiometric defects, it is divided into two parts, ma. One is metal excess defect and second one is metal deficiency defect. Let me go to the one by one in detail, ma. Right. Children, you are able to see on the screen Schottky defect. Am I right? Now, you are able to see the brown color circles, or you can say spheres now. Let us suppose this brown color sphere is Na plus. And the blue color sphere which you are able to see is Cl minus. Now, in this, this is nothing but NaCl crystal. Now, you imagine this is a NaCl crystal. Now, Na plus Cl minus, Na plus Cl minus, like this, you have the arrangement of ions. Now, exactly at this point, you are seeing a vacancy. Hope you are understanding, ma. At this point, you are seeing a vacancy, non-availability of the ion. Am I right? Actually, what ion, I'm sorry, which ion is to be present? Na plus, right? So, this defect, Schottky defect, is a vacancy defect which occurs due to the missing of cation as well as anion in order to maintain the electrical neutrality. Here the blue one, because the blue sphere is chloride ion. This chloride ion also missing from this crystal. It means what? Na plus ion is missing as well as Cl minus ion is missing. Therefore, this defect is called as vacancy defect. This defect is shown by the ionic compounds because NaCl is an ionic compound, and this defect arises due to the missing of cations and anions. Just now I explained, in order to maintain the neutrality, electrical neutrality, equal number of cations and anions will be missing. Now, children, once the ions are missing from the crystal, definitely the density of the substance will decrease. Therefore, from the Schottky defect, you can say the density of the substance decreases. Hope you understand, children. Schottky defect is a vacancy defect because it has missing out of ions from the crystal. Let us go for the next one. Right. Frenkel defect. Now you are able to see the diagram of Frenkel defect. This is also formed by ions, right? You have Ag and Cl, Ag and Cl ions present in this. Now see here, children, I am highlighting Ag here. Being Ag, it is a cation. It has the small size when compared to the chlorine. Ag have the small size when compared to the chlorine. Now actually at this point, what ion should be present? Ag plus ion. Do you have Ag here? No. Where it has went now? It got into the interstitial space. Am I right? Actually it should be present at this point, but it has moved to the interstitial space. That's why Frenkel defect is called dislocation defect, moving from one place to another within the crystal. Now, once the Ag plus is dislocating from this point to this one, you have a vacancy at its original site and interstitial defect at its new site. Am I right? That's the reason it creates a vacancy defect at its original site and interstitial defect at its new location. Now, children, one interesting thing between the Schottky and Frenkel, here no ion is moving out of the crystal. Hope you understand, children. No ion is moving out of the crystal. That's the reason the Frenkel defect do not have any change in its density. Hope you understand. Whereas Schottky defect, there is a change in density because ions are missing out of the crystal. Whereas in the Frenkel defect, obviously no, because no ion is moving out of the crystal. Let me read out once, children. This defect is shown by ionic solids. The smaller ion dislocated from its normal site to an interstitial site, it creates vacancy at its original place and interstitial defect at its new location. Now you hope understand, right? Now Frenkel defect is also a point defect. It does not change the density of the solid, right? Let me go for the metal excess defect. This is also the most important one. You will get 2 marks. What are F centers? You have a question like this. Define F centers, means what are F centers? You need to understand this, children. Now, F center. Now you have the same sodium chloride crystal. Just now I have explained in the Schottky defect. When the crystals of sodium chloride is heated in the sodium vapor, right? Sodium chloride crystal is heated in the atmosphere of sodium vapor. Now what happens? Slowly sodium atoms are deposited on the surface of the crystal. Exactly on the surface of the sodium chloride crystal, which ions will be deposited? Sodium ions. Now Cl minus ions slowly diffuse to the surface of the crystal and combine with sodium atoms to give NaCl. To make you understand, children, I have represented with an equation. Now Cl minus ions which are present in the crystal slowly move towards the surface where sodium atoms are present. Now sodium slowly loses its electron to form NaCl. The released electron, which is extra, slowly occupies the Cl minus ions, because Cl minus ions have slowly started moving to the surface. Am I right, children? Once Cl minus ions are moving onto the surface, here Cl minus vacancy is there. Now the released electron will slowly comes and occupies this particular site. Okay, let me elaborate this one. Now, this happens by the loss of electron by sodium atoms to form Na plus ions. Now, the released electron diffuses into the crystal and occupies anionic sites. Just now I explained this electron. Actually, this is the place of Cl minus, but the Cl minus has moved to the surface and reacted with Na to form NaCl, and this vacant place is filled with electrons. That's the reason you are saying here, the anionic sites occupied by unpaired electrons called F center. F center. F means Farbenzenter. It's a German word. Farben means color. What is the meaning of Farben? Color. Center. Center here, center. Colored center. Because of this one metal excess present, because of this color will get to the given crystal. Hope you understand. F centers are the anionic sites occupied by the unpaired electrons, which are called as F centers. F means Farbenzenter, which is a German word, which means color center. Hope you understand, children. Let me go for the next one. Electrical properties of solids. From here onwards, we'll be studying only the properties of the solids, which you have little bit idea in your previous classes also. But in solids, especially what kind of properties are exhibited, we'll be studying in elaborated form. Now, you know that solids are classified into three types, based on their electrical conductivity. The first one is conductors, second one is insulators, and third one is semiconductors. You know it. Conductors means it will allow the flow of electricity. Insulators, which will not allow the flow of electricity, like that you will know. But the conductivity ranges, you are not aware of it. Please remember that conductivity ranges. Conductors, you know that conductors are ranging between 10 to the power of 4 to 10 to the power of 7 ohm inverse meter inverse. Okay, these are conductors. Now, next, insulators. These are the solids which have very low conductivities. Whereas conductors 10 to the power of 4 to 10 to the power of 7. Whereas insulators, you see 10 to the power of minus 20, which is very, very less. The conductivity will be almost negligible. 10 to the power of minus 20 when compared to 10 to the power of 7. Am I right? Now 10 to the power of minus 20 to 10 to the power of minus 10. Next, semiconductors. These have the conductivities ranging from 10 to the power of minus 6 to 10 to the power of 4 ohm inverse meter inverse. Hope you understand. Let me go for the next one, children. Band theory of solids. Now, band, the term band means what? Band means a group, right? Close spaced group. Band means what, ma? Close spaced group, right? Now, according to our chemistry, during the formation of a metallic crystal, large number of atomic orbitals interact to form molecular orbitals. Children, here I want to stress a point, children. In your chemical bonding, right, we have studied about molecular orbital theory. Hope you understand that. What is that? In chemical bonding, we studied that atomic orbitals combine to form molecular orbitals. Molecular orbitals formed will be divided into, again, bonding molecular orbitals, anti-bonding molecular orbitals. Hope I am making you to recollect all those things, right? Now, please, because this is something related to that, that's the reason I am making you to recollect that. Now, a large number of atomic orbitals interact to form molecular orbitals, right? Now, if 10 molecular orbitals are formed, let us suppose, out of 10 molecular orbitals, 5 will be the bonding and 5 will be the anti-bonding, as you have studied, right? In that way, half of the molecular orbitals having the lower energy, which are called as bonding. Now, the red color one which I am showing, these are all consists of bonding molecular orbitals, right? Next, the remaining half molecular orbitals have little higher energy. Those are called anti-bonding molecular orbitals, right? Now, you can see, children, from the left upside, I am making my cursor move. No, you are able to see increasing energy. Yes, that means molecular orbitals have lower energy when compared to anti-bonding molecular orbitals. Bonding molecular orbitals have lower energy when compared to anti-bonding molecular orbitals. Now, these orbitals are closely spaced. These orbitals, you can say energy levels, I can say now onwards, because every time we cannot take 1 or 2 orbits, right? Orbitals, right? In solids, you have many orbitals together. That's the reason I'm saying their energy levels. These energy levels are closely spaced, and this is called as band. Now this band, which consists of molecular bonding molecular orbitals, now this you can call it as valence band. 1 second, children. I will show with the cursor now so that you can understand. Now this red color which I am able to show is valence band. Now valence band is the close spaced energy levels of bonding molecular orbitals. Whereas the blue color one which you are able to see, which is the close spaced energy levels of anti-bonding molecular orbital, now I can say it as conduction band. Sir, why you are saying like that, sir? Let me elaborate that, children. 1 second, let me elaborate. 1 second, 1 second, children. Please give me some time. Yeah. Now, you can see electrons can flow readily through these bands. Which bands, children? Conduction band. Why? Because you have empty orbitals in this. I have said already, this is a conduction band and this is the valence band. Now, children, the band which is formed by the bonding orbitals, as I said, it is a valence band which contains the electrons. Now, if at all electron jumps from valence band to conduction band easily, if the electron jumps from valence band to conduction band, or you can say one more, if valence band and conduction band overlap with each other, you can say that is conductor. Metals are generally good conductors. Am I right? Now, you go for the next one, children. Here, it is a valence band and this one is a conduction band. Right? Now, you are able to see some space between conduction band and the valence band. Right? This energy is called as Fermi energy. Right? This energy is called Fermi energy. Electrons, when jumps from valence band to conduction band, then only electricity will be, conductivity will be there. Am I right? Now, because of the energy difference, if you supply heat, right, now some of the electrons get energy, they can move from valence band to conduction band. Definitely it will have the conductivity property. This is what semiconductors, that's the reason semiconductors are generally acting as conductors at higher temperatures only, because when you give the temperature to a substance, semiconductor substance, it absorbs the energy and the electrons move from valence band to conduction band. Next one, children, insulators. Now, when I see insulators have taken, you see the Fermi level, so very high, and it is also called as a band gap. Okay, now when the difference between the valence band and conduction band is very high, even you supply energy also, the electron will not jump from valence band to conduction band. That's the reason electrons are not moving into the conduction band. Electrons are not possible to move. That is why insulators will not conduct electricity. Hope you understand. Let me go for this, children. Here, you are able to see that three types of structures. One is the metals, one is semiconductors, and third one is insulators. In metals, overlapping of conduction band and valence band is present. Whereas in semiconductors, there is a small energy gap between valence band and conduction band. And the third one, insulator, there's a large energy difference between valence band and conduction band. Now, let me go through this. In case of metals, these two bands overlap each other, which depends upon the number of valence electrons. Right. Let me go for this. In case of semiconductors, the conductivity increases with increase in temperature. Just now I was explaining about that, right? This is due to the migration of electrons from valence band to conduction band. Now, children, you just remember that when electron jumps from valence band to conduction band only, the possibility to conduct electricity. If there is no possibility to move from electron valence band to conduction band, in electricity is not possible in that. Now, in insulators, energy gap is large between conduction band and valence band. Thus, electron cannot jump from valence band to conduction band. Hope you understand, children. Let me go for the pure semiconductors here. Pure semiconductors whose conductivity increases with increase in temperature are known as intrinsic semiconductors. This term I'll have to explain in the next slide. That's the reason I'm just making you to aware what is intrinsic semiconductor. A semiconductor which conducts, right? Conductivity increases, right? Which conducts means its conductivity increases with what? With the increase in temperature is called intrinsic semiconductor. Let us see that. Now, children, we need to learn about semiconductors. Semiconductors are divided into two parts, right? Before I go to the semiconductors, here a word I am able to see, doping, doping. I have to explain that doping. Doping is a process of adding impurities to a semiconductor in order to increase its conductivity is called doping. Children, you can have these news. The sports person, right, have undergone doping test. Why? What is that doping? In order to increase their strength, they will take some external substance, right? In order to increase the energy or in order to boost up their energy, they will use some materials which will increase their stamina. That is called as doping, right? Actually, in chemistry also, doping means what? Semiconductors are added with other impurities in order to increase the conductivity of semiconductors. Hope you are following, children. The process of adding impurities to which one? To a semiconductor in order to increase its conductivity is called doping. Right? Now, semiconductors are divided into two types, intrinsic semiconductors. Rather, I say this is a pure semiconductor because no other external substance is added, right? The intrinsic semiconductors conductivity increases only by increasing in temperature. Rather, I say intrinsic semiconductor is a pure semiconductor. Why? Because I have not added anything. I have not added anything, but I have increased the temperature. Because of the increase in temperature, the conductivity increases. Hope you are understanding, children. Let me go for this one. Extrinsic semiconductor. In the extrinsic semiconductor, conductivity increases by addition of external substance. That process is called as doping. Just now I've explained you. What is that? Doping. Adding of external impurity in order to increase the conductivity in semiconductors is called as doping. Now, this doping is divided into two types, children. The first one is P type and second one is N type. P stands for positive type, N stands for negative type. Let me go for this one, children. Right. You are able to see a diagram. Okay. Now, P-type semiconductors. Generally, semiconductors are examples silicon and germanium. 1 second, children. I'll change my pen so that it will be visible for you. Silicon and germanium. Okay. Now, silicon and germanium are the examples for the semiconductors. Now, which group element silicon will belong to, ma? It is belonging to 4th A group, children. And how many valence electrons are present? 4. Now, if you add boron, aluminium or gallium, addition of external substance, no, because it is not belonging to the 4th group. Boron belongs to which group, children? Boron or aluminium belongs to which group, children? Third A. How many electrons are present in that? 3 valence electrons are present. That's the reason we are saying impurity. Impurity doesn't mean that which is not proper and or something. Impurity means which does not belongs to itself. It belongs to some other group. Therefore, silicon or germanium, which is a fourth group element, when doped with third group elements such as boron, aluminium, gallium, right? Then p-type semiconductor is formed. Now, how, children? How it is formed? Let me explain you in detail. Children, boron has how many unpaired electrons? 3 in the excited state, or you can say simply 3 valence electrons. Okay, boron electronic configuration 1s2, 2s2, 2p1. In the excited state, 2s orbital electron jumps into the 2p orbital, but no need of that. You have how many valence electrons? 3 valence electrons. Now, boron can form only 3 bonds, children. Boron can form only 3 bonds because it has only 3 valence electrons. Whereas the silicon, I'll be writing here silicon. Silicon belongs to the fourth A group, children. Its valence electrons are 4. So how many bonds silicon can form, children? 4 bonds. Hope you understand. Now you can see here, this boron has only 3 electrons. I'll highlight this one. Has only 3 electrons. Am I right, children? Okay. It will form only 3 bonds. Am I right? Now, when it is forming only 3 bonds, silicon is forming how many bonds, children? 4 bonds. Now you can say two electrons is nothing but 1 bond. Am I right? That means boron is connected with the silicon here. Boron is connected to the silicon here. Boron is connected to silicon here. 2 electrons is not one. Now where is the one more, dear? Where is one more electron? Where is one more electron? No, that's the reason it is showing a hole. Okay, children, because boron has only 3 valence electrons. It is not having one more electron to bond with the silicon. So you will have an empty space there. Absence of electron is called as a hole. That's the reason on screen you are able to see that acceptor impurity creates a hole. This is nothing but absence of electron. Now what happens, children, if this electron comes here? For example, if this electron comes here one hole will be there. If this electron comes here, there will be movement of electrons because of this one particular hole, right? Because of this adding impurity of the boron or aluminium or gallium, you can have increase in its conductivity, and this type is called as positive type. Why I am saying positive type? Now you got understood. Absence of electron. Electron is of negative type. Absence, opposite to that, positive type, because it is not having that electron. Hope you understand. Let me go for the next one, children. Yeah, one second, ma. Yeah, silicon or germanium when doped with group 3A, like boron, aluminium or gallium, which contain only 3 valence electrons, as I've shown. In pure silicon, each silicon is bonded with 4 silicon atoms, but dopant, the substance which you are adding from external, is called as a dopant. Aluminium, gallium, indium possess only 3 valence electrons. The 4th valence electron is required, and it is left as a hole because boron has only 3 unpaired electrons in the outermost orbit. It was not having the 4th electron. That's why it is having a vacancy. It is a hole. In this, conductivity is due to the holes. The place where fourth valence electron is missing is called as electron vacancy or hole. So children, p-type semiconductors are formed when silicon, germanium are doped with the third group elements such as boron, aluminium, gallium, and holes are formed in the p-type semiconductors. Which are formed in the p-type semiconductors? Holes. Hole is absence of electrons. Let me clear this, children. 1 second. Right. Next one. N-type semiconductors. After the p-type, now you got an idea. Okay, p stands for positive, n stands for negative, right? You can compare it, children. Now, again, the fourth group elements, silicon, germanium, when doped with fifth group elements like phosphorus, arsenic. Now, phosphorus belongs to which group element? Fifth A group element. How many valence electrons will be there, children? 5 valence electrons. Arsenic also fifth A group element, 5 valence electrons. Now, you can see, children, arsenic is forming 4 bonds with 4 germaniums. Why? Because germanium is also having 4 valence electrons. Silicon, germanium belongs to the same group. No. Therefore, it is forming 4 bonds with the arsenic. Am I right? I'm rounding off, you see, children. But arsenic has one more extra electron. Why? Because arsenic belongs to the 5th A group element. Because of this electron, because of the increase in electrons which are created by the arsenic addition, these electrons are delocalized, right? Delocalized means moving from one place to another place. The movement of, 1 second, delocalized, I'll write delocalized here, delocalized, DE, 1 second, I'll clear this. Delocalization means what? It is movement from one place to another place. Here you have, I'll just show you, children, delocalized. That electron is called as delocalized electron. Because of this electron, delocalized electron, because of this delocalized electron, you will have increase in conductivity. Therefore, whenever fourth group elements such as silicon and germanium, which is a semiconductor, doped with fifth A group element such as phosphorus or arsenic, always forms one extra electron which is not bonded to any other, and that fifth electron is called delocalized. Because of the delocalization, the conductivity increases. Let me go little bit broad, children. Silicon or germanium, when doped with fifth A group elements like phosphorus or arsenic, which contains 5 valence electrons, 4 out of 5 are used for the bonding, as I've explained. 4 out of 5 are used for the bonding with arsenic atom. 1 atom is extra. This extra atom is delocalized, right? The fifth electron is delocalized. These delocalized electrons increases the conductivity. Hence, increase in conductivity due to the negative charge. That's the reason it is said to be N-type semiconductor. Next one. Children, very, very important, magnetic properties of the solids. On the basis of magnetic properties, the substances are divided into 5 categories. Children, you already know magnetic properties which you have studied in your previous classes are only 3. What are the 3, ma? Paramagnetic substances, diamagnetic substances, ferromagnetic substances, antiferromagnetic substances, ferrimagnetic substances. You have studied only the first 3 in your lower classes. Now, you need to study about antiferro and ferri also, right? Let me elaborate one by one in detail, children. Paramagnetic substances. The paramagnetic substances are the substances which are weakly attracted by the magnetic field. The paramagnetism is due to the presence of one or more unpaired electrons and which are attracted by magnetic field. Children, paramagnetism is attributed to a solid with what? With the presence of one or more unpaired electrons. With the presence of one or more unpaired electrons, the substances get attracted towards the magnetic field. These kind of substances are called as paramagnetic substances. Now again, paramagnetic substances examples you have studied in chemical bonding. Oxygen, in anti-bonding molecular orbital, 2 unpaired electrons are there, right? Because of that, oxygen is a paramagnetic. We have studied in molecular orbital theory in chemical bonding. Now in addition to the oxygen, copper plus 2, Cu plus 2 ion, Fe plus 3 ion, chromium plus 3 ion will all exhibit paramagnetism. Now the red color arrow marks you are seeing, children, right? What are these? These are spins, children. What are these? Electron spins. One is in clockwise direction, another one is anti-clockwise. Clockwise, anti-clockwise. Now you can see how many clockwise are there? 1, 2, 3, 4. Anti-clockwise only 3. I can say number of unpaired electrons are more, the paramagnetism is more. They are not paired up. Now, diamagnetic substances. Already you know, children, diamagnetic substances are weakly repelled by the magnetic field. Diamagnetism is shown by those substances in which electrons are paired. Now, unlike paramagnetism, paramagnetism is because of unpaired electrons, whereas diamagnetism is because of paired electrons. Now, in this one, do you have any unpaired electrons? No, children, all are paired. These two are paired, these two are paired, these two are paired. All the electrons are paired. That's the reason if a substance contains no unpaired electrons, then it is said to be diamagnetic substance. Hope you understand, children. Examples for diamagnetic substances: NaCl, benzene. Benzene formula is C6H6. Now, let me go for this next one. Yeah. Ferromagnetic substances. Now, ferromagnetic substances, paramagnetic substances, a little difference. Ferromagnetic substances are also formed by unpaired electrons only. Paramagnetism is also formed by unpaired electrons only. But ferromagnetism can be made into permanent magnets. Ferromagnetic substances can be made into permanent magnets. Now, let me give you the clarity, children. A few substances very strongly attracted by the magnetic field, such substances are called ferromagnetic substances. What do you mean by that? Few substances are strongly attracted, he's saying, right? Now, when the substances are strongly attracted, definitely what happens, ma? They'll be made into permanent magnets. So that's the reason here, besides strong attractions, these substances can also be made as a permanent magnets. Example, iron, cobalt, nickel, etc. Now you can see all the unpaired electrons present in the ferromagnetic substances. Let me go for the next one, children. Anti-ferromagnetic substances. Here, from this point, you'll have little bit confusion, because antiferro you have not yet came into in understanding now. Antiferro is a new term for you actually. Antiferromagnetic substances are the substances which have the structure similar to the ferromagnetic substances, but their domains. Domain means combination of spins is called domain, right? The total small tiny combination of spins is called domain. Their domains are oppositely oriented and cancel out each other. I said domain means a small collection of spins, right? They will cancel each other means what? Whatever the number of positive direction domains are there, the equal number of opposite domains are also there. Therefore, the net magnetic moment is equal to 0. Example for that, children, manganese oxide, MnO. So antiferromagnetic substances, you just remember that it is similar to the ferromagnetic substances, but the net magnetic moment is equal to 0. The net magnetic moment is 0. Let me go for the next step. Ferrimagnetic substances. In the ferrimagnetic substances, ferrimagnetism is also observed when the magnetic moments of domains in the substances are aligned in parallel and anti-parallel directions. Children, ferro, ferri, anti-ferro, right? You have different terms. Now, in the ferrimagnetism, the domains in the substances are aligned. Aligned means placed in parallel and anti-parallel. Parallel means one is in the clockwise, the other one is anti-clockwise. That's the reason I am mentioning the term called as parallel and anti-parallel directions. Now, do we have the same number of parallel and anti-parallel in ferri? Your answer will be no. Why? Because the net magnetic moment is not equal to 0. It means what? The total magnetic moment not equal to 0 means the number of clockwise direction domains are not equal to the number of anti-clockwise domains. That's the reason ferrimagnetism, the net magnetic moment of ferrimagnetic substances are not equal to 0. Example, Fe3O4. Right, this is a ferrimagnetic diagram, children. You can see the red color one is in the clockwise domain and the blue color one is in the anti-clockwise domain, children. Now, let me explain you what we have learned in the today's session, children. Packing efficiency. Because of the time, I have explained only the simple cubic one. We have even body centered and face centered. So, right, in the packing efficiency of the face centered is 74%. Packing efficiency of body centered cube is 68%. And packing efficiency of simple cube is 52.4. Right, now we have studied about the density of the unit cell and its problems. Density, what is the formula? D is equal to Z into M by NA into V. Based on that, we have done problem. Next one, very important, children, imperfections in solids. We have imperfections stoichiometric as well as non-stoichiometric. In the stoichiometric, we have studied about SCOTTKY and FRENKEL. Next, we have studied electrical properties. In the electrical properties, we have studied the band theory. Very, very important, children. Band theory. So, 1 second, children. 1 second, I'm sorry. Right. The last one is magnetic properties. Now, just I'm giving you the self-practice so that you can see this class and you can have the revision, and whether you are able to do these problems or not on your own, let you check it. In terms of band theory, what is the difference between semiconductor and a conductor? You can write what is the difference between semiconductor and a conductor based on the band theory. What is the energy difference between semiconductor and a conductor? Right. Next, what is a SCOTTKY defect? I have explained you, very important, children, for 4 marks. For what is SCOTTKY and FRENKEL defects, very important. Next, what is FRENKEL defect? SCOTTKY defect is a vacancy defect. FRENKEL defect is a interstitial defect. It is not completely moving away in FRENKEL. In FRENKEL defect, what is happening? Atom or ion moving from its own place to interstitial space. What are F center? Right? F centers, I have explained you that German word. Explain ferromagnetism with examples. I have given you examples and I have explained you ferromagnetism. Next, explain paramagnetism with examples. Right? Explain p-type semiconductors and n-type semiconductors. So once you go through all these, children, so that you can understand it, if you have any doubts, please ask your respected teachers. I've tried my level best to make you understand in a short time. If you have any doubts, you can ask your teachers, as well as you can write in the comment box. Definitely we'll reply to it. Thank you, children.
Thank you, Aravind, sir.
Thank you, ma'am. Thank you.
It was a very wonderful session, sir. So thank you for explaining the solid state physics, solid state chemistry in a very easy manner to all the students. Children, please go through the webinars of solid state, so which was taught you from past 3 days. So please try to learn the Bragg's equation. And then yesterday, sir discussed about the So yesterday we discussed about the Bragg's, day before yesterday we discussed about the Bragg's equation, isn't it?
Yes, ma'am. Yes, ma'am. Bragg's equation in the first session,
yes,
octahedral and tetrahedral in the second session.
Voids. Yes, sir.
Yes.
Yesterday, sir discussed you about the octahedral and tetrahedral voids, and today he clearly explained you about the defects in solids, right? And
Yes,
please learn the magnetic properties of solids also. See, children, they are also very important for you in your for your objective examinations and also for your IP examinations. So, children, please go through this webinar sessions and write down the notes and learn properly. So, once again, I thank Aravind, sir. So, sir, you explained very clearly about this topic. Why? Because it is a bit difficult to understand, because it is a perception. Yes, yes, it is an imaginary one. So it is very difficult, but you explained in a very clear manner. So thank you, and thank you one and all for giving us this opportunity. Thank you, sir.
Thank you for the webinar team for giving me this opportunity. Thank you one and all.